Let's see if Tiger has any helpful advice. Ring ring.
Wojskaż by.
Tiger says.
Bitwam se dasy na trusem. Nemi svani poveće beda te eba. Toponar.
Well, that didn't go very well, did it? I bet you feel even more alone now, don't you, Giraffe? You're probably thinking about graduating from weekend roast potato binges to weekday gin tonic benders, aren't you? No, Giraffe, that's not the way. Probably. Now look, the world is awful at times. It really is. The only thing I dislike more than living here is myself. But that's okay. We all get the blues sometimes. It'd be weird not to, considering how strange everything is. Perhaps the real problem is that we've built a culture where we aggressively enforce the idea that confronting the sad truths of the world is unhealthy or weird, despite the fact that we all do it, that we have to, and that actually, at the bottom of it, underneath kind regards and birthday cards, everybody is a total mess. And you should be one too. So there's about 8 billion of us little parasites at the moment, and average life expectancy is around 26,000 days, which means that chances are about 300,000 people are having the worst day of their entire lives today. And isn't it nice not to be one of them? But it will come our tennis upward, of course. And what does one do when one's life falls apart? How the hell will I know? Do I seem like a happy person to you? But we might want to talk about this obscure composer you won't have heard of, who in 1876 wrote to his nephew saying, "Indeed, my life is of little worth to anyone. Were I to vanish from the face of the earth today, it would be no great loss to Russian music." That was actually...
Hey everyone, welcome back, and let's write some more neat code today. Let's look at a sliding window problem, a hard sliding window problem, sliding window maximum. The statement is pretty straightforward actually, so we're given an array of numbers, and we also are given a number k, which is going to represent the size of our sliding window. It starts at the very left and then works its way to the right, and so since it's size k, there's only going to be k numbers inside the window, and for each position that the window is in, we want to return the max value. So you can see that this is our input array, and our window is going to be size 3, so this is our first window, and the maximum value is 3. So then we see, and then we add a 3 to our output array. So the output is going to be an array. Next we see that this is the next position of the sliding window, and the maximum value in this case is still 3. So we put a 3 in our output. And the next position we see that this is our window, the maximum value is 5. So we put a 5 in the output. Now, you might recognize one solution to this problem immediately. For each of these windows, why don't we just scan through the array, right? Like, it's pretty easy to find the maximum in an array, right? Like, if we had 1, 2, 3, we just check every value and see, okay, this is the maximum. And then we just shift our window by 1 into the next position, right? And we keep doing that until we're done. Well, the time complexity of this is going to be roughly, since the size of our window is k, how many windows are we actually going to have? Let's say the entire input is length n. In that case, we're going to have roughly k times n minus k. That's how many windows we're going to have, right? And so this is going to be our time complexity. But I'm asking, is there a better solution? Can we actually make a linear time solution where n is the size of the input array? And the answer is yes. And I'm going to show you how to do that right now. So I'm going to show you the best solution, but one thing you have to notice first is this. So let's say this is our input array. We have 4 numbers and our window size is going to be 3, so k equals 3. Notice how these values are in increasing order, right? 1, 2, 3, 4. Okay, so we notice that. Now look at our first window. We have 1, 2, 3. We see that 2 is greater than 1. We see 3 is greater than 2. Now that's good. And so we scan through every element. 1's not the max, 2's not the max, 3 is the max. So then in our output, for the first value, we're going to put a 3. Okay, and that's great. Now we shift our window to the next position. So now I'm literally just going to repeat that process the brute force way. Now I'm going to check 2, okay. Now I'm going to check 3, 3 is greater. Now I'm going to check 4, 4 is the greatest. So we add 4 to our output. And so then we're done, we have our output, but we just did it the brute force way. But do you see the repeated work that we just did? As soon in our first window, we saw 1, 2, 3. We know 3 is greater, so we basically eliminate 2 and 3. And then when our window is at the next position, it's over here, right? 1 is no longer a part of our window, so we don't need to worry about 1. What about 2? Well, 2 is inside of our window, right? It's at the leftmost position. But since we know that this 3 is greater than the 2 anyway, why would we ever need to look at the 2 ever again? It's never going to be the maximum. And let me just make it even more obvious. Let's say our window size is 6 and this is our input array. Okay, so for our first window, we have to check, okay, the 1, another 1, another 1, another 1, another 1, and then a 4. So the 4 is our max. That's great, so we can save that. And then we shift our window to the next position and see we're repeating all that work over again, the 1, 1, 1. As soon as we see this 4, we know that these elements, as far as we're concerned, are useless to us. We never have to look at them again. They will never be the maximum inside of our window because our window is going to continue being shifted to the right position and the 4 is still going to be in the window even after these elements have been eliminated. And so the data structure we're going to use to eliminate these values is a DEQ or a DQ. And I'm going to show you the algorithm. And just to repeat myself, basically what I'm saying is if we have a window and we see a value that's greater than values that are previously in our window, then we can eliminate those values from our window. And so I'm going to show you the algorithm, and what you're going to notice is that the values in our DEQ are always going to be decreasing order. So this says decreasing. So we know our window, our sliding window is initially size 6, right? K equals 6. So we're going to take the first one, put it in our window, the second one, put it in our window, and then just repeat that, right? We have 5 ones, we're going to add all of them, and then we get a 4. So since 4 is greater than the value at the top of our DEQ or at the rightmost position of our DEQ, what we're going to do is we're going to pop this value off. What we're going to do is pop the top of the DEQ, right? And now we're going to make the comparison again. We see there's still a 1, so 4 is still greater than the top of our DEQ, so we're going to pop. We're going to pop this, we're going to pop that, we're going to pop all of them, and after that, we're going to add the new value 4. And so what are we going to add to the output? So we have an output array. What value are we going to add to it? Well, the leftmost value, and in this case we only have one value, is going to be what we add to the output, so a 4. And so we're done with this comparison. We don't have to look at it again, and we don't even have to consider these elements anymore. And now we shift our window by 1 position. So we're introducing a new element, 5. So before we add the 5 to our DEQ, what do we have to do? We have to check, is 5 greater than the value at the top of our DEQ? It is, because the top value is a 4. So why would we ever consider the 4 as the maximum value ever again when we know there's a 5 right next to it? The answer is we don't have to, so we remove the 4 from our DEQ. And then we can add the 5 to the top, and then we know that there's only one value in our DEQ, and it's also the leftmost position. We are going to add that to our output, and now we're done. This is our output. But what's the time complexity of this algorithm? First, we took each one, added it to our DEQ, right? We did that for every single value. That was expensive. And then we also crossed out. We had to remove every single value from our DEQ. But adding and removing, we know adding and removing is an O of 1 operation to our deck, and we had to do that for every single value in here potentially, but that's still O of n, right? The result is O of n, which is why this is a really good solution. And I'm going to show you one last example, and by the way, this is called, the type of problem this is called a monotonically decreasing Q. And the reason is because our Q is always going to be in decreasing order, which this next example is going to demonstrate. And the reason we're using a Q rather than a stack is because we want to be able to add and remove elements from the beginning in O of 1 time. But not only that, as our window shifts, like for example, our window's here, next our window could be here, we want to be able to take an element like this and remove it from the beginning. And we want to be able to do that in O of 1 time, which is why we need a Q. So let me quickly just run through this last example. So we have our first window over here, 8 and 7. So we add 8 to our Q. Then we look at 7. Well, 7 is not greater than 8, right? That's just not true. So we're allowed to add the 7. We only want to remove smaller elements if they exist, but in this case, that's not true. So we add the 7. And notice how these values are in decreasing order. We have 8 and then we have a 7, right? They're in decreasing order. So what that tells us is since we want the max value in our sliding window, we can just look at the leftmost value in our deck and then add that to the output. So I'm going to add 8. For the first sliding window, the max value happens to be 8. Okay, now the next sliding window, we have 7 and we have 8. Okay, the first thing to notice is that the 8 is no longer in bounds. So we got to pop from over here, right? And we want to do that efficiently, which is why we're using a deck. But so before we add anything, we pop. Next, we see the 6. Well, 6 is not greater than 7. That's not true. So we're allowed to put a 6 here to keep this in decreasing order. And now the max value in this window is 7, which is the leftmost value in our deck. So we add it to the output. And lastly, we look at the last sliding window, which is these last 2 elements. And we know that the 7 is no longer in bounds, right? So from the leftmost position, which is this, we pop from our deck. We make one last comparison, right? We just added a 9. Let's take a look. Is 9 greater than the top value of our stack? Is it greater than 6? It is. What does that mean? That means we have to pop from the top of the stack, the rightmost position, or rather the queue. I don't know how many times I said stack, but we're going to pop from the rightmost position in our queue. And now we are allowed to take the 9 and append it to our queue. So we add the 9 now. We know that this is the leftmost position in our queue, and we know that in this window, 9 is the maximum. So we did this correctly, right? So we can take the 9, add it to our output. So this is the result that we're looking for, and I hope this demonstrates a few of, like, when you actually run through examples, it shows you like what you need to know. It shows you why we're using this data structure, and it shows you why it's so efficient. So now with that in mind, the coding solution is not too bad. So we are going to have an output array deck, and so we're going to run this until our right pointer is no longer dead, and we're going to represent where our window currently is. They're both initially going to be set to 0. And we're also going to have a Q in Python, you write R. And instead of doing nums of R, I'm just going to do the index itself. So this is going to contain indices, because we know we can take an index like R and then easily find the number that it maps to by just taking nums of R, right? But before we're even allowed to append a value to our queue, we have to make sure that no smaller values exist in our queue. So while the queue is non-empty and the top value in our queue, or the rightmost value in our queue, is less than the value that we're in. The rightmost value in our queue is less value in our queue, or the rightmost value in our queue is less value. So while the queue is non-empty and the top value in our queue, or the rightmost value in our queue, is less than the value that we're inserting, nums of R, which is the current index we're at. So while smaller values exist in our queue, we just want to pop from the queue, just remove values while that condition holds. And only after we do that are we allowed to add the new value to the queue. We also, if our window, if the left value is out of bounds, then remove the left value from the window. So if our left index, left, is currently greater than the leftmost value in our queue, then we can pop from the left of the queue. So basically, we know left and right represent our window. So if our window is if this value, the leftmost value in our queue, is out of bounds of our window, we're going to remove that. We have to remove that. And this part is our window is if this value, the leftmost value in our queue, is out of bounds of our window, we're going to remove that. We have to remove that. And this part is kind of an edge case. Since we are starting at our window being left and right both being at 0, we have to check that our right plus our window is at least size k. So if we want to update the output, we have to make sure our window is at least size k. So that's basically what I'm doing here. And for each iteration of the loop, basically for each window, we want to append our output with the maximum. So we know the maximum is the leftmost position in our queue. And we want not the index, but we want the actual value itself. Don't forget, like me, to update your pointers. So we know right is always going to be incremented. So at the end of our loop, we can increment right. Left, though, is only going to be incremented once our window is at least size k. So we're going to put that inside of this condition. And now the only thing left for us to do is we're going to put that inside of this condition. And now the only thing left for us to do is return that output. And it works, and we know that this is the most efficient solution with the time complexity being linear and
Okay.
can